Welcome to Aerosim Gaming. I'm Rush, and this is the first video in the test flight series on the F-86 Sabre in DCS. This first video is going to cover the ground school side of things on this aircraft, where I'm going to cover the aircraft systems and how I can manipulate them. I, however, won't be covering the weapon system of this aircraft, where instead I'm more focusing on how to fly the aircraft precisely and well enough before turning it into a weapons platform. You might ask why. Why would I spend the time learning about all the individual systems in the aircraft if I'm not really flying the real thing? Well, I believe that in simulation we strive and we demand more and more realism from our simulators. And I believe having a better understanding of how the real aircraft behaves in real life versus simulation will give us better models. Because I think everyone that is watching this has probably had issues flying an aircraft in a simulation where things happen that just shouldn't. So with this kind of video, we can have a good in-depth look at the systems, the aircraft, and then how it performs. In regards to the performance, I'm going to push the aircraft beyond its limit. It's all really easy to just have a look at the aircraft flight manual in real life and then just go fly this aircraft within that envelope. But where things start breaking down in simulators is outside of that bubble, where it seems to be we hit a brick wall, where I believe this series will be able to go through that brick wall and make aircraft developers develop the aircraft to where they can fully be capable in their flight envelope. Anyway, enough of the introductions. We'll start the video by having a look at the external model of the aircraft. We'll start here on the right hand side and move our way along. You can see that this aircraft does not have the automatically deployable leading edge slats that some of the later model Sabres had. It does have a wing fence halfway along the wing there, and that's to stop spanwise flow. So what that tells me is that as the aircraft gets a little bit slower, or the angle of attack increases, is that the ailerons start becoming less and less effective. Or at the stalling angle, the ailerons become completely ineffective. The wing fence there is designed to stop that. We'll see that when we get in the air and see how it goes. Also we'll notice, as we can see, is all the gear doors are down. The gear doors being down is telling me that there's no hydraulic power on the aircraft. As soon as hydraulic power is restored to the aircraft, those doors will automatically close. We'll move to the rear of the aircraft here. We'll see it has standard regular flaps. They are electrically controlled, and we'll get into those systems later when we get into the aircraft. Also, we'll see the speed brakes are left open here. That's standard on all Sabres. The reason being is for maintenance staff to get in the tail there. There's a lot of hydraulic reservoirs and accumulators in the back here, and those need to be accessed after flight. We'll move further along the tail here. We'll see here at the tail, we actually have an all-moving tail plane. So as I move back on the stick, the tail plane will completely move as well as the elevators. And that was to help with the high Mach numbers this aircraft flies at. Continuing the walk around here, there's nothing really else to note. It's a very, very basic airframe on the outside. You see here we've got some drop tanks installed, and this is just to help illustrate the fuel system when we get into the cockpit. As we move around to the front, you'll see it, you can't see it, but there's a little door directly under the pilot on the lower part of the fuselage. That door is where the ammunition is loaded, but it also serves a secondary purpose, as that's how the pilot can climb into the aircraft. It's almost like a ladder. And right at the nose of the aircraft, we'll zoom right in here, is we'll see that there's a probe. It almost looks like a pedostatic probe at the front there. That's actually for the fuel control unit on the engine. It actually tells the engine how much air is coming into it, so it knows how much fuel to add. And that tiny little circle you see just at the bottom of it, that's actually the cooling intake for the starter generator. And in any real pre-flight, the pilot would poke his head all the way in there and have a good look at the blades. A thing that is missing from the model that we can see here is directly to the lower part of the intake. What you can see there is that's actually where the gun camera would be mounted on the real aircraft, but in game it's obviously not modeled. We'll have a look at the overview, the overall size of the aircraft here. The aircraft is actually built in 4 sections. There's the forward fuselage, the 2 wings, and the tail. The engine actually mounts just aft of the cockpit there. And if I zoom right in, I can see the split in the fuselage. Right through that yellow band, you'll see a rivet line and a line that wraps around the whole of the fuselage. That's actually where the tail detaches, and I'll just throw a picture in here so you can see how the engine installs and how the tail actually attaches. A thing to note is the tail, it's held on by 4 bolts. That's it, 4 bolts. But they are pretty big bolts, so there's no issue of the tail falling off this aircraft anytime at all. Just before we jump into the cockpit, what we'll point out here, just with a nice little picture, is that the cockpit is fully pressurized. So once a canopy is closed and the canopy seal is inflated, the cockpit is completely pressurized up to 5 psi. What that means is up to about 26,000 feet, you'll maintain a cockpit altitude of 14,000 feet. Why this is important is for the damage model. Is if I take a bullet through the canopy and it doesn't hit me, there should be a rapid depressurization of the cockpit, which would include frosting over and condensation building inside the actual cockpit, which would completely remove the visibility out of the cockpit. First thing we'll look at in the cockpit here is the electrical system of the aircraft. It's quite a basic system, just consisting of a pair of batteries and a generator attached to the engine. The battery and the generator provide power to the primary bus and the secondary bus. The primary bus handles things like the fuel boost pumps, bomb release, engine ignition, speed brake control, fuel quantity gauges, and stuff like that. Where the secondary bus handles things like the gun heaters, the cockpit temperature control, all the ancillary stuff of the aircraft that are not really important. However, these two are completely connected together. The electrical system in the F-86 is controlled in the front right-hand pedestal with the single battery switch. There is also a guarded generator switch, which is usually left down at all times, unless of course there is a failure of some sort. The electrical system can be monitored on the left-hand lower side of the instrument panel. There we can see the electrical output from the generator, and also we can see the load that the aircraft is putting on. What I mean by load is how many things you've got turned on. There are several warning lights associated with the electrical system scattered throughout the cockpit, and those include the generator warning light on the lower part of the instrument panel, and then there's several on the upper part of the warning panel, which is the main inverter failure. If the main inverter fails, basically all your primary flight instruments will start to fall off. Anyway, once either ground power or the battery switch is turned on, the primary and secondary bus are energized and the aircraft is alive. A thing to note here about the electrical system is the 2 batteries are installed just ahead of the pilot here, just in front of the cockpit. They're actually above the intake, and the generator is obviously attached to the engine. The thing here is redundancy. So if I lose my generator, my batteries now will take over the electrical load. Why that is important is the alternate hydraulic system. If you lose all the hydraulics on this aircraft, your backup is your electrical system. So if you have both a generator failure as well as a hydraulic failure, your batteries are the only thing left that will get you back home. And with really gentle control inputs, maybe you'll have about 30 minutes of flying time. But also a thing to note is your electrical load. If you have your landing lights turned on, you start pulling your flaps out and stuff like that, which is using your electrical power that's left in the batteries, you will not make it back home. It's very, very important here that you really look after your batteries, especially in the case of a hydraulic failure. The next part of the ground school is going to cover the fuel system. The fuel system of the aircraft can be summarized as having 5 main tanks, with 2 fuel boost pumps in the forward fuselage lower tank, and 1 transfer pump in the rear aft fuselage tank, with the rest of the fuel tanks actually feeding by gravity into the lower forward fuselage tank. Of course, the internal fuel can be supplemented by 4 drop tanks stored on outboard storage stations on the aircraft. The drop tanks are pressurized from bleed air from the engine and feed fuel into the main forward fuselage tank. As each tank is selected on the drop tank selector valve on the forward left-hand side of the cockpit, it opens a valve on the corresponding inboard or outbound drop tank, which allows compressed air from the engine to pressurize the tank, which allows fuel flow. However, fuel flow does not start instantly, In fact, it takes the forward fuselage tank to drop 56 gallons, and then it will allow fuel from the external tanks to flow and top off the center tank. The fuel quantity gauge on the lower right hand side of the instrument panel only shows fuel remaining of the internal stores of the aircraft. There are two indicators that tell you when your external stores are empty. One is an orange light on the left hand side of the store selector panel, and also the fuel quantity gauge will start to decrease. This is actually really important to know. As soon as the external stores are empty on this aircraft, you're actually at a fuel critical state. With an average fuel flow of 3,000 pounds per minute, at 3,000 pounds of fuel remaining, you can assume around an hour's worth of flight time until you will run out of gas completely. The next system or systems of the F-86 we're going to have a look at is the hydraulic system as well as the flight controls. And that's because the two are very closely linked, as this aircraft's primary flight controls are all controlled by hydraulics, except for the rudder. And this will be a good thing to note later when we start looking into failures and stuff like that, as the only flight control in this aircraft that will continue to work when everything else is not is the rudder. But anyway, let's have a look at the rest of the system. The aircraft actually has three hydraulic systems. It has a normal system, which handles all of the flight controls, including the all-moving tail, the elevator, and the ailerons. And it also has a utility system. And the utility system handles everything else, including the parking brake, the landing gear retraction, nose wheel steering, as well as the speed brake. These are two completely separate systems, all powered by two separate engine-driven hydraulic pumps. Of course, with any aircraft there has to be some kind of redundancy, and there is. There is an electric alternate system, and this alternate system runs off battery or generator power and provides hydraulic pressure to the flight controls in an emergency or system failure. I'll start here with the alternate hydraulic system. The alternate hydraulic system automatically comes online when the normal hydraulic system pressure drops below 700 psi. What that does is it provides hydraulic power to the flight controls, the ailerons and the elevator, and we can monitor that system by the hydraulic pressure gauge in the upper left hand side of the instrument panel. We'll see there's a 3-position switch just to the right of it, which allows us to select the utility, normal or the alternate system. And all that does is it just changes what the gauge actually displays. It changes what system the gauge displays. But while here sitting on the ground without the engine turning, I can see that the alternate system is on, and I can confirm that by looking out the window here and moving the controls. But as we'll see, as I move the controls vigorously, that pressure drops down quite substantially. And this just shows how the system cannot be relied upon, or your flight control movements have to be minimized to maintain the hydraulic pressure long enough to get back to base. As I said, the alternate system automatically comes on. There is also a manual override, and that manual override is on the right hand side below the engine control panel. And when you pull that lever, it completely disables the normal system. Let's say it was damaged in battle damage or something like that, and completely reverts to the alternate system. What we can see from the schematic that I have here of the flight control hydraulic system is the alternate system actually has two hydraulic accumulators. And why that's useful is if you do have to revert to the alternate system, is that there is far more hydraulic fluid available in that system than there is in the normal system. What I will show here is also the engineering schematic diagram of the hydraulic systems. That's the normal and the alternate system put together. What you can actually see from this drawing is you can see where the actual flight controls attach to the hydraulic actuators on the flight controls. Also, we can see that the two systems are completely separate with two complete separate hydraulic lines. Why this is important, again, is when it comes to battle damage. I don't know how it happens in the game, but it would need two systems to be completely shot out. Not only that, but the system has enough in reserve that even if a return line was shot out, that the hydraulics would continue to work until all hydraulic fluid is exhausted or lost overboard due to battle damage. There is also a nifty little device actually in the alternate system called the compensator. And what that is it's actually an 8-inch in diameter piston that sits in the tail of the aircraft, and that piston is held in place by spring tension. What that spring tension does and that piston does is it actually maintains a constant pressure or a constant feed of hydraulic fluid in the system. So if there is all of a sudden a large requirement for hydraulic pressure, that the compensator is able to absorb that rather than the alternate system electric pump. I, however, don't believe this is well modeled in game. As we can see when I move the flight controls, there is an instant hit to the hydraulic pressure, but in reality that doesn't really happen. The compensator actually helps with that. Until, of course, you've used all the remaining pressure that's available, and then it takes time for the alternate system pumped to recover that pressure. Anyway, so let's have a look at the utility hydraulic system. So as I said before, the utility hydraulic system covers things like landing gear retraction, brakes, what else have we got here? Speed brake control, sorry, and of course nose wheel steering. I'm going to show an engineering schematic here of the landing gear retraction and extension system. And the thing to note here is just how complicated it is. There's actuators on landing gear doors, there's secondary actuators on landing gear. It's an incredibly complex system, but in the cockpit you wouldn't know it. Why is this important though? Why do I need to know what the landing gear extension and retraction system is like? Well, really you don't. But what you do need to know is what happens and I have to do an emergency extension or an emergency retraction. And let's just quickly touch on that emergency retraction. That is actually a thing. In game, it is not modeled correctly. Actually, if you hover over the button, it says ground use only. This is completely incorrect. The aircraft actually had this installed on it for an emergency landing. What sort of emergency landing, you ask? Well, it would be an engine failure right at liftoff. This aircraft is quite slow on the ground. It has a pretty bad power to weight ratio. And what they found during testing is that if an engine failed and the gear was down, the aircraft simply would not stop. So this emergency retraction system was added. The whole idea was that once your nose was off the ground, you would jettison all of your fuel tanks and stores and at the same time lift up, push the button for the emergency retraction and then land on your belly, with the belly helping you slow down a hell of a lot faster than your wheels will. So this item really should be modeled in game. I mean, I know some people don't have the random failures turned on, but in case you did have an engine failure right at V1 or that rotation speed, is this item here, this emergency retraction, is very, very important, especially on the shorter runways that sometimes we operate out of in the game. A thing to note with the emergency retraction is it actually only sends hydraulic pressure to the retraction side of the hydraulic actuators on the gear. It does not send any hydraulic pressure whatsoever to the gear doors. So what this actually does is it slams the undercarriage through the undercarriage gear doors, completely breaking them in the process. But then again, this is for an emergency and you are about to put an aircraft down on its belly. Moving on from that, we'll have a quick look at the rest of the undercarriage. Basically, there is an emergency extension. The emergency extension is not as damaging to the aircraft as the emergency retraction, where basically the uplocks holding the gear doors are removed and the gear's own weight knocks the doors out of the way. This does not damage them in any way, but still would require maintenance staff to have a look at it when you got back on the ground. I think I'll leave it there for hydraulics for the time being. If there's any other questions or comments, please let me know and I'll record anything else that we need. So we'll have a quick look at the engine that powers the F-86 now. There's really not too much to talk about a turbojet engine. They either work or they don't, with everything in between just meaning the engine is not serviceable. So the engine that powers this aircraft is a J47 non-afterburning turbojet engine. It has a 12-stage axial flow compressor with 8 combustion chambers and just a single turbine at the end. I'll just put up a little picture here just showing where the cold section or the compressor section is at the front of the engine, which is in blue, and then the combustion chamber, which is in red. And there's 8 of those combustion chambers wrapped around. This is obviously just a cutaway. The white point in the center is the hottest part of the engine, where the actual flame of the combustion chamber is, and the yellow part is showing where the air is starting to cool and expand as it exits the tailpipe. The engine should produce 6,100 pounds of thrust at sea level, and everything else in between we'll look at in flight. Other than that, there's really not too much to talk about. I mean, I could go into jet theory a little bit, but I don't think it's worthwhile going about in this video. It's something I could probably cover at a later date, but for the scope of this video, it's just not required. The engine either works or it doesn't. So what I'm going to do now is just get the aircraft up and running, and we're going to start the engine here. The actual startup procedure is quite easy because most of it is automated in the background systems. So what I'm going to do is I'm just going to show a fuel schematic just as an overlay here, so you can see what parts of the engine fuel system are turning on or turning off as we go through the startup sequence. The thing to note here is the yellow is not where the fuel is currently. The red is where the fuel is allowed up to, and the yellow is basically just showing where the fuel will get to eventually. So what I'll do here is I'll go ahead and I'll turn the engine master switch to on. What that does is it energizes all of the start and engine systems. It doesn't actually turn them on, so the fuel pumps are still off and all the things like that. But now what happens is as I press the outboard function to get the throttle outboard, is what I do there is I open up the fuel stop valve, and I also turn on all of the fuel pumps. However, the fuel stop cock, yes, that's what's actually called, is not actually on yet. And what that means is there's no fuel getting to the engine. However, by moving the throttle outboard, as we go here, there we go, we can hear the fuel pumps turn on. Now when I flick the starter, we should see N1, our engine percentage here, get to about 3%. So we'll flick it on here, and there we go straight to 3%. We're going a little bit above 3% here. What should not be happening, which is happening right now, is there should be no fuel flow and there should be no EGT, because this valve here is not open yet. Anyway, so what we'll do is we'll allow fuel to get through to the engine, and we should hear light off and the engine should happily start away. And what we're doing while we're watching is we're just monitoring the EGT here, making sure it doesn't go above 950 degrees, and just monitoring fuel flow. And we can see the speed here is increasing slightly. If the engine is going to hang or it's not going to accelerate, this is about where you'll see it to hang, around this sort of 23% mark. As we can see, it's just starting to accelerate past it. There we go, EGT stabilised and RPM is stabilised. Look, what I'm going to do here is I actually have an external video of the Sabre getting started up where it used to work. So I'm just going to shut up and let you watch that video so you can hear it, because the sound is amazing and nothing beats a fiery jet engine start. Okay, so as you can see, we're in the aircraft and it's up and running. We'll just make sure we flick over to battery there, and we'll close up the canopy here to just make it a little bit quieter. So the things to note in the startup there is the EGT and the fuel flow do not behave like the real aircraft. There should be no fuel flow and no EGT on that first outboard movement of the throttle. They should not happen until you move the throttle to the second time, because that second time, that's where it opens up the final stop cock, or fuel cock, whatever they call it, which allows fuel into the actual fuel manifold, which provides fuel to the combustion chambers. Anyway, after everything else is set up here, is what we can go ahead and do is just do some basic engine tests here. So one of the tests I've got here is straight from the maintenance manual of the aircraft, which is, I'm going to hold the brakes here, bring the power up to 70%. It actually says 70 to 75, so we'll pick somewhere in between. We'll go 75. So what I should be seeing at 75, I should be seeing an EGT of 400 degrees or 450. And you can see in game we are just not seeing that. We're way below. The other thing that I should be seeing is a fuel flow of 2,000 to 2,600 pounds. And we are way below that. The engine is nowhere near using the right amount of fuel on the ground. Anyway, what we'll do is we'll take that up to 100%, and at 100% I should be seeing an EGT of 690 degrees. So the EGT is just about right on, we can see there. It's actually a little bit high. And we can also see the fuel flow is just on 5,000 pounds. Anyway, what we'll do is I'll just bring the power all the way back down. There's no real need to burn a whole heap of virtual fuel. Also, after the engine start, we'll see that our hydraulic system here, the alternate light, is still on, and that's just because we haven't reset the flight controls. We reset that just with this switch down here, reset them, the light goes out, and we can go ahead and have a look through all of the hydraulic systems here. We can see the engine-driven hydraulic system is all around that 3,000 psi, and the alternate system is just a bit below at about 2,700 psi. So I think that just about covers it for the first video in the test flight series. Any of the schematics and stuff like that I've used, I'll just leave a link down in the description if any of you guys or girls would like to have a look over them. The other thing to note is I am aware that I have missed out a few systems here. I'll cover those as we turn into the flight side of this test flight, which will be in the next video. The things that I am not going to cover are the circuit breakers. I've tried using them and they don't seem to really do anything. They work on some systems, but I tried using them specifically to do a cold start on the engine and they just don't work. I also tried using them on the inverters for redundancy with the flight controls, and I couldn't seem to get that to work either. There are a few issues that I found while doing this series, which I'll probably put a post up of a bug report of the things that I found, but none of them are game breaking, of course. There's just a few little things that just don't quite replicate the real aircraft. Anyway, thank you so much for watching. I will ask for a few things from you guys that are watching, as this is the first video, so I'd really like if I could get some feedback whether this video is worthwhile, if there's too much information, not enough information, or if I should go a little bit more in depth. The other thing to note is this just too much talking and not enough flying? That is another note to sort of give me feedback on, if that's okay. As always though, thank you for watching. I really appreciate your time watching this video, and have a great day.